Let's see this question which is asked in GATE 2011 paper. So by solving this question, we try to understand the difference between interrupt driven IO and direct memory access. Okay. So first of all, we see this question. Already you know the question, right? Please read it. After that, try to understand the solution. So there are 500 bytes of data which device is producing. We have to send it to memory. For that, interrupt driven IO is doing like this. We know that interrupt driven IO, in that device once generates the interrupt, then CPU will come to execution. That means CPU will execute interrupt service routine, right? That interrupt service routine is given in the English, okay, in high level language, but they are saying that assume that each such English language statement as one machine instruction. Okay, we will see that. So what that interrupt service routine is doing is, first it is initializing the address register. Okay, assume that this is your main memory. So your CPU is initializing one dedicated address register. Okay, fine. We don't know how much time it will take. We will just assume that it takes some time. Initialize the count to 500. There is a variable called count. That means there is a register called count register. So that is updated with 500. Okay. Next. So these machine instructions will be executed. So interrupt driven IO is nothing but executing one small program. That program is this one, right? But that program is executed only after interrupt is generated by your device. So now loop begins. Load a byte from device. So this is let's say your device. So from the device, so one byte, assume that somewhere it has that byte, then that byte will be loaded into some temporary register. Let us take another register. So let us say that byte is B1. So B1 will be loaded into that register. So we assume that this device is a device like a hard disk, maybe, because we are transferring 500 bytes, right? Maybe you can assume hard disk or something, okay, whatever. Now we will be loading that byte from this hard disk to some temporary register. So that is what load a byte from device. We will be loading a byte from device. Next, store it in memory at address given by address register. So this address register specifies one memory address and you go there and write that data. You see now, because of this final instruction store, now data which is at our CPU is stored in 100 location, right? This is a way data transfer is happening with lot of instructions, right? Now next, increment the address register. So we have to increment the address register. Let us increment it to 101 because it is byte, we are transferring bytes, right? Since your machine is byte addressable, next byte will be at 101, right? So after that, decrement the count. Yes, we have to decrement because we have to keep track of number of bytes to be transferred. So we will do that. Then we check this condition. If count not equal to 0, yes, count not equal to 0, then go to loop. In that way, 500 times this will be executed, right? So whenever count is 0, we stop. Then these instructions are executed 1, 2, 3, 4, 5. How many times? 500 times, because for every byte we do that, right? Now by this time you understand how interrupt driven logic is working. Now we will see. Assume that each statement in this program is equivalent to machine instruction which takes one clock cycle to execute. So they have clearly mentioned that this process, if you see, so each instruction takes exactly one machine cycle, right? See here, one clock cycle. So let me count the number of clock cycles. For this instruction, one clock cycle, will read completely equivalent to machine instruction which takes one clock cycle to execute. If it is a non-load store instruction, we know load and store instructions. You see, this is a load instruction because we are loading a byte from device. Okay, so assume that this is a load instruction which takes 2 cycles. Next, store also takes 2 cycles, right? So how do you know that, sir? You read this one. A non-load store instruction takes 1 cycle. Otherwise, the load store instructions take 2 clock cycles to execute, because I know the question, I have written it. Now, incrementing the address register, decrementing the count, and checking this count, everything are very easy to do, right? So they take less time. So that's why they have mentioned it as 1 cycle. Okay. Now, so now the question is, we have to, yeah, you understood finally it is interrupt driven IO, right? Let us read the remaining question. DMA approach. There is another approach called DMA. In that, what they did is we know that initially we have to prepare the DMA controller, right? 20 clock cycles for initializing the DMA controller. You know that. What is the story about DMA access? There will be a small controller, DMA controller. So this is your CPU. Whenever CPU gets interrupt, then CPU will give that work to DMA controller. So DMA controller now will have all this stuff, right? Address register, data count, everything. Okay. So data address register, data count, everything. Okay. Now initially CPU will give everything to DMA controller, my dear DMA controller. So this is the address register. This is the data to be transferred, 500, everything. Now just continue. Now from now onwards I give you bus, you continue. That is the story. Okay. For that, this entire process is called initialization. That initialization takes how much time? 20 clock cycles. By these 20 clock cycles, your CPU is busy like executing these instructions. Okay. So to do all this stuff, we have to write a software, again, that is, I can say DMA routine. Okay. So DMA routine takes 20 clock cycles to do all this stuff through program. But that program is not given in the problem. And other overheads, they did not mention other overheads. There will be some other overheads. Maybe once DMA transfer is over, we have to interrupt the CPU, right? Everything is 20 clock cycles. Now each DMA transfer cycle takes 2 clock cycles to transfer 1 byte data from device to memory. He has clearly mentioned once you prepare your DMA controller, then DMA controller takes what? 2 clock cycles to transfer the 1 byte data from device to memory. See, each DMA transfer cycle takes 2 clock cycles to transfer 1 byte of data from device to memory. To transfer the data from device to memory, so 2 clock cycles are required. Now the question is, what is the speed up you get because of this DMA, right? For that, first of all, we have to see the overhead, otherwise time required to execute interrupt driven program. After that, we have to see time required for DMA approach. Let us focus on the first case. What is the time required to do this interrupt driven program first? Okay, let us do that. Now we'll see one by one. First we see interrupt driven. In interrupt driven, if you see, initialize the address register. This is one step, right? One cycle, that is clearly mentioned. Initializing the count to that 500, that is also one instruction. It takes one cycle. Now if you see, these two are only executed one time, but this loop is executed how many times? 500 times, because there are 500 bytes. For every byte transfer we are doing this, right? So I can say that this is executed 500 times, right? Now 2 plus 2 4, 4 plus 1 5, 6 7, 7 cycles are required in each loop. There are 500 iterations, so 500 into 7, 3500. This code is executed 3500 times, right? So that's why 500 times. So each time 7 cycles, that's why 3500 cycles plus these two, only one time. So 2 instructions, 2 cycles. 3502 clock cycles are required if you use interrupt driven IO. Now we'll see DMA. If you see DMA, they have clearly mentioned that 20 clock cycles for initialization and other overheads. If you see, each DMA transfer cycle takes 2 clock cycles to transfer 1 byte data from device to memory. Generally speaking, so this is an ambiguous question. In DMA transfer, after every byte transfer, CPU will not interrupt the DMA. But here they have mentioned that each DMA transfer cycle takes 2 clock cycles to transfer 1 byte data from device to memory. So they said that after every byte transfer, again CPU intervene, and CPU wastes its time of how many clock cycles? 2 clock cycles. So what I want to say is, if really this is the DMA model, because in general DMA model, that won't happen, that is not the way we do, but in the question they have mentioned we have to follow, otherwise you don't get the answer. That's a problem. Okay, so first of all, let's try to solve this problem by only assuming that this 20 clock cycles is the overhead. Okay, in the exam, how to solve the questions, though they are ambiguous, I will tell you. You have 4 options, one of them should be correct, right? Otherwise question is wrong, you get the marks, right? Assume that question is correct, then DMA transfer requires only 20 clock cycles. because initially we set up everything, right? So that setup takes only 20 clock cycles. Then what is the speed up you get over this interrupt driven IO is, the formula is, what is the, if you want to know the speed up of DMA, then formula is, what is the time required for interrupt driven IO? 3502 cycles divided by, number of clock cycles here only 20. Then it's supposed to be around 175, right? But there is no 175 speed up. That means this is wrong. Then what should I do? We should think carefully. They have mentioned that one more thing, 2 clock cycles are required for 1 byte data transfer. So for every 1 byte data transfer there is a CPU overhead, let us say. Then 500 bytes if you want to transfer, every time 2 more clock cycles. So 500 into 2 cycles, 1000 cycles. Assume that these 1000 cycles also, for these 1000 cycles also CPU is busy, plus initially 20 clock cycles for initialization. Initialization will be done only once, so it would be 1020 clock cycles approximately, isn't it? So 1020 clock cycles. Let us divide this time by 1020 clock cycles. Then one of the option definitely matches, right? So if you simplify it, I think you get around 3 point something, right? So 3.4 is the speed up. In that way we can solve this question. See this question which is asked in GATE 2016 paper. The size of the data count register of a DMA controller is 16 bits. Okay, this is 16 bits. Now the processor needs to transfer a file of 29,154 kilobytes, kilo means 2 to the power of 10 bytes, from disk to main memory. Yes, we understood. The memory is byte addressable, fine. The minimum number of times the DMA controller needs to, minimum number of times, you remember that, okay? So the controller needs to get the control of the system bus. You know one thing, right? Example, let's say you have 500 bytes of data to transfer. The minimum number of times we need a bus to get the control is only one time. Why? Simple, your CPU will load this count register with 500 value, okay, and necessary details will be given to you, okay. Then you will be transferring the data. Further you will be asking the system bus, you will be taking the control over this bus, right? So one time is enough. Sir, why one time? Why not 2 times, 3 times? See, the question is about minimum number of times. If I use burst mode, so at a time entire data I can transfer, whatever the data I have I can transfer, right? Sir, if that is a question, then for this also answer should be 1. No, the reason, we have fuse file, right? 29,154 into 2 port 10 bytes. Your CPU cannot mention that in your DMA controller, because the count register has a limitation of only storing 16-bit data. So what is the maximum data size you can store is, see, if you write 500 here, then DMA controller understand that data to be transferred 500 bytes. But maximum I can write 2 to the power of 16, right? Minus 1 approximately. Exactly 2 power 16 minus 1, but approximately 2 to the power of 16 is the highest value we can write. So if I write it only at most to 2 power 16, then that means what? 2 to the power of 16 bytes. That means what? That is a trick here. Only 2 to the power of 16 bytes at a time we can transfer, because the count register can accommodate only that capacity, right? That's the only, you can mention only that size. So now we have a huge file which is greater than 2 power 16, correct? Then what we do is, first of all we transfer 2 to the power of 16 bytes of data using burst transfer. Then later we'll say CPU, my dear CPU, reinitialize this. In that way it has to reinitialize so many times. Example, you have 2 into 2 power 16 bytes of data, then 2 times we need a control over the bus, right? So it's all about how many 2 to the power of 16s you have. That's why you divide your file size 29,154, this is your capacity, into 2 power 10. Because of the limitation of your count register, at a time only 2 to the power of 16 bytes can be transferred. But you have 29,154 into 2 power 10 bytes, then how many times we have to reinitialize this one? So that many times we will be freshly taking the control over the bus, right? So probably that is what the question, by understanding the question, so that is the best way we can understand it, right? So if you simplify it, 2 power 10, 2 power 6, right? So it would be 29,154 by 64, right? If I divide 232 is 2, 14, 28, 1, 2, 5 are 10, 1, 15, 2, 7 are 14 and 2, 7 are 14, right? It would be 14,577 by 32. If I divide it, it would be probably 32 fours are 128, right? So 32 fours are 128. How much you get? If you see 32 fours are 128, it's a, I mean, just we can do like this 1 4 5 7 7. It's all about simplification. 32 fours are 128, 15 minus 8 7, 3 minus 2 1, right? 17, 177. 32 fives are 160, that would be the right number. Then it would be 17, then again 177, it would be again 5, 13 fives are 160. You get this time 17 again, but digits are over, then we have to take point here, then it would be 170. 32 fives are 160, right? Almost 455.5 times. That means 455 times we have to take the control plus one more time, right? Approximately it would be 456, right? Answer is 456. 455 full times. The last time, the 0.5 means some few data will be there which is less than 2 power 16, right? That will be final time. Let me ask one question. If you have 2 into 2 power 16 bytes of data plus some 5 more bytes, then how many times we have to do that? For 2 power 16 one time, because you have 2 power 16s 2 times, then for this 5 bytes one more time, 3, right? That's why here also 455 times plus this, because of this decimal point, one more time, right? 456. Answer is 456. See this question which is asked in GATE 2005 paper. A device with data transfer rate 10 kilobytes per second is connected to a CPU. Okay, you have a device which is connected to CPU. Okay, this is your CPU. These two are connected. So data is transferred byte-wise, and one more thing, that data transfer rate from this device is 10 kilobytes per second. Remember it. Fine. Now data is transferred byte-wise. That means a device is going to send only one byte at a time. Then later another byte in that way. The speed of each byte is like this. Using this is a speed 10 kilobytes per second. Now the byte transfer time between the device interface register and the CPU or memory is negligible. So whenever you want to transfer the byte from the device register to CPU register, this is your main memory. You know one thing, right? Whatever may be the idea, like it is program driven IO or interrupt driven IO finally. So once data is ready, then we have to transfer that to CPU register, then later CPU register to main memory, otherwise directly from this IO register to main memory. But whatever it is, the time required is negligible, 0. But then most of the time where you spend is the question, right? In program driven IO, the time we spend is just polling, right? Because recall program driven IO. However, I know the question. You also read the question completely, then you understand the question first. What is the question you see, so that you can understand my motivation, why I am talking about the time requirements. Because in the question they have mentioned that what is the minimum performance gain of operating the device under interrupt mode over operating it under program control mode. In the program control mode, how much time your CPU will be wasting, we will see. CPU will be completely wasted, I can say, correct? So we will see what CPU is doing. So CPU will be checking, there will be a special bit, that is data ready, correct? Already I told you in basic IO management, right? Please attend my basic IO lectures where I taught program driven IO, interrupt driven IO, then easily we can understand. So in program driven IO, what happens, there will be a bit called device ready or data ready. So we will check that bit. Initially that will be 0. Then your CPU will have a program that's why program driven IO. So the program, what the program's intention is, that instructions will be designed such a way that instructions are seriously checking this bit. Whenever this bit is 1, then immediately we take the data. But unfortunately this bit cannot be 1 unless data is ready. So the speed, so the data's availability depends on the speed of the device. Let us see. The speed of this device is 10 kilobytes per second, correct? So before going to this calculations, I will tell you the strategy of program driven IO. In the program driven IO, using the program instructions, some machine level instructions, we will be checking this bit, okay, for some time. Then suddenly that bit will become 1 whenever data is ready. So whenever data is ready, immediately we transfer it. For that we are not taking any time because that is negligible. So that is a story. In that entire story, where are you spending in checking this bit? So this bit, whether it is 1 or 0, depends on the speed of the device. Let us, that's why, focus on speed of the device. My dear device, what is your speed? I can send 10 kilobytes per second. Okay. Then how much time you take for 1 byte? We will see. This device takes 10 kilobytes. It can send in 1 second. Then to send 1 byte to this register, how much time it will take? It would be 1 byte by 10 kilobytes. If I simplify, byte gets cancelled, it would be 1 by 10k. 1 by 10k, if you simplify, k is nothing but I can write 10 cube. Okay. So it's all up to you, like 2 power 10 I can write sometimes, 10 cube, it depends on the calculations. Okay, both are almost equivalent. So 10 cube is nothing but I can say, if I send it to top, it would become 1 by 10 into 10 power minus 3. Minus 3 is nothing but millisecond, right? So remember it. Finally 1 by 10 millisecond, it would be 0.1 millisecond. So what I want to say is, your CPU is busily checking this bit, right? So that bit cannot be 1 up to this duration, 0.1 millisecond. Example, let's say your program has started. Okay, so it would be like this. For every 0.1 millisecond, 1 byte will be ready, but by that time what CPU is doing? Busily waiting for data by checking this bit. After that, 1 byte will be transferred. Then again we have to check this bit for the next byte. Then again it takes 0.1 millisecond. So finally 0.1 milliseconds it is required for your CPU in this model to transfer 1 byte. Remember it. Now there is a second model. What is that second model? The second model, if you see, that is interrupt driven IO in that. So what is given? Anything is given. What is the minimum? See here, the interrupt overhead be 4 microsecond. That means in the interrupt driven IO, the model will never check this bit, but your IO device will just give the interrupt for us, right? So what I can say is, whenever interrupt is generated, only at that time your CPU starts working. Then at that time directly your CPU will go to that appropriate interrupt service routine, and that will be executed. That is called interrupt overhead. That is 4 microsecond. So finally in interrupt driven IO, only when interrupt gets activated we will work, then only 4 microseconds of time we spent, right, for 1 byte transfer, because for every byte, whenever it is ready, interrupt will be created or generated. So I can say that in the interrupt model, 4 microseconds are required for your CPU to invest for 1 byte of data. But if you see program driven IO, 0.1 milliseconds per 1 byte of data. Then if you want to know the speed up, right, here also what is the minimum performance gain? If you want to know the performance gain of your interrupt, let me write like this. Performance gain of interrupt, if you want to know, formula is what is the performance, otherwise what is the speed you achieved through program driven. Always you remember, because it is between program driven and interrupt driven, right? So interrupt driven versus program driven, if you want to know the performance benefit, then find out the time required in the program driven and divide it by time required for interrupt driven, right? Okay, interrupt driven. For 1 byte we can calculate, because number of bytes are not given. So we can assume we can calculate all this stuff for 1 byte. To transfer 1 byte in the program driven, how much time is spent? Let me write here, 0.1 millisecond, right, divided by, in the interrupt driven, what is the overhead? 4 microsecond. If you divide it, you get performance gain. Okay, now did you remember in pipelining system also, if you want to know the performance gain of pipelining model, then formula is time required for non-pipeline divided by time required for pipeline. Similarly, if you want to know the performance gain of interrupt driven program, interrupt driven IO, then you divide the you take first program driven IO and divide that by interrupt driven IO time. So for 1 byte transfer, 0.1 millisecond, here 4 microsecond. So if you divide it, you get the ratio, otherwise performance gain. It would be, if I simplify, 0.1 into 10 power minus 3 seconds, I am converting into seconds, by 4 microsecond is 4 into 10 power minus 6 seconds. If I simplify, it would be 0.1. I can write, let us write 0.1 divided by 4 into 10 power minus 3 by 10 power minus 6. 10 power minus 6, if it goes up, it would be 10 power 6 into 10 power minus 3. So 10 power 6 into 10 power minus 3, it would be 10 cube, right? So it would be 0.1 into 10 cube by 4. Let us simplify further. So 10 cube, 1000 into 0.1 is 100 by 4. So 100 by 4 is 25. So final answer is 25, right? So option B is the right choice. In that way, we can answer this question.